All right, so remember, uranium-235, 238, and 239 are all different isotopes of the same element. And of course, since they're above element 83, they all are, they undergo fission. Sorry. All right, so remember I was mentioning Leo Szilard and coming to the United States and meeting up with Einstein. Now Einstein was already world famous. He was very very famous. He of course came up with his famous E=mc², which is basically a way of understanding how the nuclear bombs actually worked. Believe it or not. Where does the energy come from? It turns out that mass itself is, you can kind of think of mass as frozen energy, right? And mass can be converted into energy, and energy can be converted into mass. Now, that does take place. It's usually on the subatomic level, but this thing that Szilard had envisioned while he was crossing the street in London one day, and basically forced his hand to come visit Einstein in the United States in New Jersey. The other thing that I didn't mention before in the last video is that Einstein was a lifelong pacifist. He did not believe in war. He had of course fled Nazi Germany, but he realized, at least when he published this letter, or he sent the letter to President Roosevelt, he realized that that Nazi Germany. I think Szilard probably convinced him that Nazi Germany, if we didn't work on the bomb first, the United States, of course, then Nazi Germany was going to do it. And in fact, there's a very famous German physicist that worked for the Nazis, that helped discover quantum mechanics. His name is Heisenberg, Werner Heisenberg. And Heisenberg came really close to discovering this chain reaction, but fortunately for the world, he did not, and the Nazis never had the nuclear, an atomic bomb. All right, but Einstein's contribution to the bomb is a little bit exaggerated, other than coming up with a theoretical formula that explained what was going on. He didn't really have anything to do. Absolutely did not have anything to do with the development of the bomb, or the engineering that went into it. That was a different generation of scientists working in Los Alamos, New Mexico. It was very secret, very hush hush. The Manhattan Project. The general public had no idea what was going on. But by the way, the Manhattan Project, it wasn't just in New Mexico. There was actually some of this went on in Savannah River. What would become, if you ever go to the um, you know the Augusta, right? If you've ever been to Augusta, Georgia, or North Augusta, which is in South Carolina, there's this huge nuclear power plant there. That's the Savannah River Nuclear Power Plant. That's actually where we developed some fissionable material. That was one of the first breeder reactors. Because there's not a lot of uranium-235, right? Uranium-238 you can't make a bomb with. You don't get the chain reaction, right? It's only there's only certain fissionable materials that you can do that with. Plutonium is an example as well, and it took us a while to develop plutonium. All right, so you basically get greater energy, the greater the mass of the particle. That's the whole E equals mc squared. The mass of the nucleon outside of the nucleus is greater than the mass of the same nucleon that is bound inside the nucleus. And the reason for this is there's this binding energy that goes on. The greater mass in the nucleon, the mass of the nucleon outside of the nucleus is greater than the mass of the same nucleon bound in the nucleus. The greater mass of the nucleon is evident by the energy required to pull the nucleon apart from one another. That's also known as the binding energy. All right. So anyhow, when the nucleus loses mass in a nuclear reaction, that loss of mass, that delta M, is multiplied by the speed of light squared, and so there's you lose a little bit of energy, you get an enormous return in energy. And chemical, like a stick of TNT, for example. There's a little bit of this going on, right? But only when you get to nuclear reactions do you get a large fraction of mass turning into energy. All right. So the graph. This is a graph of the nuclear mass versus the atomic mass of the elements from hydrogen to uranium. Notice this is sloping upwards, and then there's a slight curve because of the disproportionality of neutrons. So there's got to be more neutrons in these more massive atoms. Which of these nuclei has the greater mass, right? Of course, it's going to be uranium. You just got to look on the periodic table for that, right? So uranium would be way, way up here. So if we divide, so this is an interesting situation. So this is a very, very famous graph. If we divide the mass of the nucleus by the number of nucleons, you get mass per nucleon. All right. So think about what that is, right? You got the mass of the nucleus, right? And then you divide by the number of the nucleons. And you get this curve right here. And notice the bottom of this curve is right at iron, element 26. So it turns out, so basically what this curve is telling you is if you go let's take this extreme, this right hand side. That would be the element uranium, and if you undergo fission, right, you will gain energy. You're going to get energy all the way down to iron. Right now, going from in this direction, this top atom up here would be helium, of course. That's the lightest element, and then comes I'm sorry, the top one, of course, would be hydrogen. The next one would be helium, and so forth, right, down the periodic table all the way to element 26. Now, if you go this way, if you go from hydrogen to helium, helium to lithium, or actually, it generally goes helium to carbon. This is something that takes place in stars, by the way. This process going down this way is called fusion. So if you create heavier elements, and notice that this is a much steeper curve, you get a whole lot more energy, right? And so if you go in this direction, right, then you get this huge amount of energy, and that's the difference between. So this going this way is fission, right? And fission works going all the way to iron, but then fusion, right, is going this way, and you get more energy until you get to iron, and then it takes more energy. Like you only get energy down to iron, right, to element 26. If you try to do fusion beyond that, you don't get any energy out of it. Although, of course, the stars that explode at the end of their lives. We'll talk about this much later. In what's called a supernova explosion, can turn their iron into all the rest of the elements on the periodic table. That, in fact, that's where the elements come from: dead stars, right? Mostly it's this stuff right here: carbon, nitrogen, oxygen, and carbon, nitrogen, yeah, really, hydrogen, carbon, nitrogen, oxygen. So the typical fusion of stars. All right, so let's see. So which of these? So it says here, in which of these nuclei does the proton have the greatest mass? Remember, the more massive, the smaller the nucleon, right? The nucleons have to be smaller because there's all this binding energy. And so, of course, that would be hydrogen, right? Because hydrogen's all by itself. If you take like what's called hydrogen 1, there are actually 2 isotopes of hydrogen. There's hydrogen 2, which is called deuterium, and hydrogen 3, which is called tritium. Anyhow, the hydrogen would have it would be the largest. All right, it would have the greatest. All right, let's see. Yeah, there it is, hydrogen. Let's keep moving here. Which of these nucleons? So, in which of these nuclei does the proton have the least mass? All right, and so you actually have to look at this picture right here, and so you see where this is what this is showing is the mass of the nucleus by the nucleon number, the mass per nucleon, right? So the mass per nucleon, where it's the least is, of course, iron. All right, so that answers that question. Oh no, that's the wrong one. Yeah, so there it is, iron. All right, yeah, so they're just showing you that. Remember, this side is going down this way. This is called fusion. Going this way, that's called fission. That's really important. All right. Nucleons in hydrogen 2 has more mass. Nucleons in helium 4 has less mass, right? Because it has more binding energy. The graph of the nucleons per nucleon number versus the atomic number for uranium. The nucleons in uranium nucleus have more mass than the nucleons in the uranium fragments, right? Because, of course, the fragments are further down. They're approaching. They're starting to approach iron. That's why. Nuclear fusion. Okay, so remember we're talking about this side of the periodic table. Or, sorry, not the period. This side of this graph, right? Which is kind of reflecting the periodic table. This is hydrogen. Down here is iron. All right. So anyhow, fusion is the combination of nuclei of lighter elements to form heavier elements, right? So it's going this way. Fission is heavier elements breaking down into lighter elements. All right, so that's that. Any nuclear transformation that moves the nucleus towards iron releases energy. Iron is the nuclear sink because you don't get any energy when you go past iron. And that has to do with what goes on in stars. We'll talk about that much more at the end of the semester. So thermonuclear fusion, right? 1952 was the first hydrogen bomb, which is the first thermonuclear bomb. It was basically the United States was the first one to explode one of these things in a little place called Bikini Atoll in the South Pacific, and that was the first, basically creating a star, for an instant, a star on the planet Earth.